We're going to revolve this region R, bounded by all of these functions about the x-axis, and we're going to find its volume. Let's draw a picture first of what's going on. We have an e to the negative x function, which looks something like this. X equals 0 is the y-axis, y equals 0 is the x-axis, and then there's this x equals the natural log of 10 right here. The natural log of 10 is just a number. So we have this region here that we need to rotate about the x-axis. And the way that we do this is we split this region into little tiny pieces, and we rotate each one of those pieces around the x-axis. You'll notice that when we rotate this little tiny slice of this region, we get a circle. And when we rotate every single slice of this region, we get a lot of circles. And ultimately, this three-dimensional volume is going to look something like this. Now, each one of these little slices has a thickness of dx. And after we rotate this slice around the x-axis, it becomes this really thin cylinder. It's a circle with just a little bit of thickness to it. And the volume of each one of those little tiny cylinders is going to be the area of that circle. That's pi r squared times the thickness of that cylinder, which is dx. Well, the radius of each one of these little circles is given by the value of this green function, e to the negative x. So our radius is going to be e to the negative x. So the volume of each one of our thin cylinders is going to look like pi e to the negative 2x dx. If we want to find the entire volume, well, what we have to do is add up the volumes of each one of those little tiny cylinders. The way that we do this is we take an integral. We're going to integrate from x equals 0 all the way over here to x equals the natural log of 10, and we're going to integrate pi e to the negative 2x dx. We're going to complete this integral to find the volume, but you'll notice that what we did is we just used what's called the disk method, and the disk method has many variations, but if we're rotating about the x-axis, this is the version of the disk method that we're using right here. Now, to complete this problem, we need to integrate and plug in our limits. I'm just going to pull the pi outside. The integral of e to the negative 2x is negative 1/2 e to the negative 2x. If you're wondering about that integral, specifically where the negative 1/2 comes from, what we technically did is we used the u substitution. U equals negative 2x. du is negative 2 dx, and then the dx in that integral becomes negative 1/2 du, and that is where that 1/2 comes from. I'll let you work that out. I'm going to simplify this a little bit, and I'm going to plug in our limits of integration. Simplifying this first limit is kind of tricky. This exponential and this logarithm want to cancel each other out because they have the same base, but we have to get that negative 2 out of the way. And you get that negative 2 out of the way by using that property of logarithms. The second term can be simplified by remembering that e to the 0 is just 1. Now this exponential and this logarithm cancel, giving us 10 to the negative 2 power. And there are a number of things that we can do now to simplify this. Remember that 10 to the negative 2 power is 1 over 100. We could factor a negative 1/2 pi out. Simplifying what's in the parentheses means finding a common denominator. And finally, I'm getting 99 over 200 pi as my final answer. That would be units cubed because this is a volume. So I'm going to zoom out on that so you can see all of the work that we did. I hope that this helps you out with the disk method and finding volumes of revolution. We'll do another one in the next calculus problem of the day. I'll see you there.